Okay, so I guess we should get started. So my name is Chen from Fudan University of China. So I'm in charge of this session. So this tutorial talk will be given by Dr. Arnab Sen. He will tell us about numerical approach to fluctuating magnets.
Okay, so so as Gang said, I'll be talking about numerical approaches to magnetism. So of course, it's a very vast field, so I won't be able to cover everything, but just to tell you some of the stuff which I feel more comfortable talking about, and then there'll also be a lecture following mine by Yasser Iqbal where he'll talk about some other things. So, okay, so well, frustrated magnetism is a very hard field in general. So, of course, there is no one technique through which you can solve all its problems. And normally what one does is one uses something to gain some insight and then uses something else to gain some other insight into such difficult problems. And numerical methods like these form one class of very important tools in that respect. Okay, so various powerful methods exist, but as we'll see in this talk, each of these numerical techniques has its own advantages and limitations. Okay, so just to name a few, I think all of you must have heard of all these things, but in this talk, at least for some people who might not have seen some of these, I'll just try to demystify these, and we'll even see applications to interestingly strongly correlated phases. So, so one very interesting class of methods, which when it works beautifully, is the Monte Carlo set of techniques. And here I'll discuss both classical and quantum Monte Carlo. And another technique, which of course gives you a lot of information, is exact diagonalization, because basically you get the wave function itself, and you can even get excitations and stuff like that. But of course, the restriction here is of system size and so on and so forth. But if you look at the right quantities here in exact diagonalization, you can still, even with small system sizes, get lots of interesting insights. Okay, so I would also focus on that. So these are the sort of the three things I would sort of cover in my next 1 hour. And there are various other things which are very important as numerical techniques. For example, if you go to one-dimensional systems, Monte Carlo methods have this great limitation called the sign problem, which we'll see what it means in this talk. But if you are in 1D with local interactions, then typically these DMRG techniques avoid that. And it many a times can even give you dynamical information, which Monte Carlo techniques cannot. So that's a really powerful technique, but I won't have the time to discuss that. Then there are various other things like series expansion techniques, various kinds of series expansions, then variational wave functions, and so on and so forth. So I think Yasser will also touch on this in his set of in his lectures, so on variational wave functions and other things. Okay, right. So let's start with exact diagonalization, because yeah, that's easiest to start with. Right. So here, basically, the concept is very simple. You have to solve you have a many-body local Hamiltonian on a finite lattice, and you have to solve the eigenspectrum problem given the Hamiltonian, right? Because the Hamiltonian is local, therefore, what you land up with is a sparse matrix eigenvalue problem, right? Because it can, I mean, if you just take some basis, let's say you consider spin half and then take the SZ basis, then if you act the Hamiltonian on any of the basis states, it can just locally flip a certain number of spins, and then in that sense, it's a sparse matrix. Right? So when you do exact diagonalization, you don't have to write your full algorithm, in the sense that there are very, very sophisticated program packages which people can use for matrix diagonalization. And this is one of the most well-known, LAPACK. And the nice thing about this is it's free. Okay, with these kind of things, you can basically get the eigenstates. And if you have the eigenstates, of course, in principle, you can solve for any static or dynamic quantity for the quantum problem that you're interested in. You can also solve it at finite temperature by just calculating the partition function and calculating things like susceptibility at finite temperature. But of course, there's a big problem here. If life were so simple, you could have just used it to solve everything, right? So the big problem is that the matrix that you get, the size of this matrix becomes very large, extremely fast with the number of degrees of freedom in your system, right? So let's imagine a spin-half system. So for simplicity, in this talk, I'll just focus either on spin-half systems or on classical spin systems, which will have some unit vectors or so on, just for simplicity, okay? So if you take a spin-half system, of course, you can easily see that the number of basis states that you require for solving this matrix eigenvalue problem grows as 2 to the power n, where n is the number of spin-halves that you have. So if you want to do a full diagonalization, and you're not using some very clever techniques of parallelization, etc., then typically what you can handle is a matrix of size around 10 to the power 4, okay, if you want to do full diagonalization. That roughly gives you n is equal to 20 spins, if you consider spin half. And the effort to diagonalize goes as m cubed, where m is the dimension of your Hilbert space, right? So you can see that, of course, you cannot go to very big system sizes here. So it's really important to look at the right quantities if you're doing exact diagonalization. That's one message I'll try to give during the few slides on ED that I would show, okay? And I would call exact diagonalization ED from now on to save time. Okay, so that's one thing. You can glean useful insight for small system size systems in many cases. The another interesting thing, which is also very important, is ED can help you test the correctness of some other more complicated techniques, right? For example, suppose you write your own quantum Monte Carlo code. You of course need to at least know whether your quantum Monte Carlo code is right or wrong. Then you can use data from ED and do your quantum Monte Carlo at some very small system size and compare both of them and see whether it's correct or not. Okay? Good. So one of the things to stress in ED is it's really important to, when given a problem, try to identify its symmetries and then try to block diagonalize the matrix according to those symmetries, right? For example, suppose I take the Heisenberg model on a 1D chain, and let's say I apply periodic boundary conditions. Then you can immediately see that there are already many conservation laws that you can use. For example, you can use total spin conservation, you can use total spin conservation in the z direction, you can use momentum conservation because there's translation symmetry, so on and so forth, right? So these symmetry resolved eigenstates are very useful because not only do you know the eigenstate, you also know the right quantum numbers associated with it. And from that, you can actually try to calculate the dispersion of excitations. As I'll show in this talk, this is also very useful. This symmetry resolved information is also very useful in detecting symmetry breaking in the thermodynamic limit. Even though you might think, oh, these are very small systems, how on earth can I detect symmetry breaking? But it'll actually be very useful. And you can even locate critical points to great accuracy in certain one-dimensional systems, if you just look at the right quantities. If you just look at the full eigenspectrum, you may not detect any of this, okay? Good. Oh, and by the way, at any point if something is unclear, just stop me, okay? So, right. So as I said, we'll just be talking of spin-half systems. So for spin-half, it's particularly easy to think of a basis. There's a natural basis, which may not be convenient for all possible problems, but the natural basis is, let's say, you take the SZ basis. So, and that's a complete basis. So you just represent the basis as up spins or down spins, and on a computer, you can just represent them by binary objects like this. So it's very easy to program it. So of course, if you go to higher spin problems, then you have to think a bit more carefully of what you want to do. But for spin half, there is a natural choice. Okay, right. So now, let's think of some simple conservation laws. Let's first think of the easiest conservation law. Let's say the conservation of magnetization in the z direction, so mz. Now that's very easy to check because this quantity is actually a diagonal operator in this basis, right? So given all the basis states, you can just compute the total mz in all of them, and you can just order them according to, you can just put your state in the right mz bag if you wish, right? And of course, if there is a problem where mz is a conserved quantity, then there'll be no matrix elements of H between states with different mz. Okay? So it's very easy to do this counting. For example, suppose I have a basis state where there's n up spins and this is n down, which is the number of down spins. Then the size of this mz block basically goes like this, because that's the number of ways of choosing up spins and down spins. Okay, and you can easily verify yourself that the largest block is then mz equal to 0. So then, just to compute this number, if you have 24 spins, the largest mz equal to 0 block has these many states in it. And this is, of course, a much smaller number than the full Hilbert space dimension, right? Good. Now, that's just one symmetry, right? Now you can use the other symmetries which might be there in your Hamiltonian, and split these blocks further and further, right? So you can split this block into smaller blocks, and then so on and so forth, right? So let's, for example, look at translation symmetry, because that's another example, that's another symmetry which is present in most undisordered problems, which you might do on the lattice. So just to give an example of that, so what do we mean by the symmetry? So basically, we have the translation operator, which I denote by T. And let's say these are again some spins living on a one-dimensional ring. And I call it a ring because there's a periodic boundary condition here. So basically, this T operator just moves the site index by 1, right? And if you just imagine the system on a ring, this operation would just give you this, right? So you just move once in the ring. So now we just need to construct basis states n such that these are eigenstates of this object, right? Now clearly the original basis of up-down spins or 1, zeros, etc. does not satisfy this property because there's clearly a shift. So I want to make basis states like this, right? So where of course this momentum is discretized because you're on a finite lattice. So now there is a way to do that, and the way to do that is basically well known. You just apply this translation operator repeatedly on any representative state, and you just have to weigh it by the correct momentum factor, right? And then if you just take this state and you apply this operator T on it, you can easily verify for yourself that it will give you back this. So that's a straightforward exercise. So just to give you an example, consider 4 sites, right? Then I go to this bit representation. You might have, let's say you start with the representative state 0, 0, 1. You just do this operation once. So of course you get this state back, right? Because you just push this one here, then you do it again, then you do it again. Now this is a 4-site ring. So clearly if you do it once more, you'll come back to the original state, right? Because they're just 4 sides. So if you do t to the power 4, that's identity, right? Okay. So then, you see, you just don't need to consider these 3 states after that because they're all related to this state by translation symmetry, and you can just talk of constructing momentum states with the right k vector, just starting with this representative state. And then you don't need to even worry about these states, right? So you can already see how the Hilbert space dimension is getting smaller and smaller. Okay, now there can be some interesting class of states where, for example, this guy, where you do a translation once, then you do it again, and you actually come back to this state, right? So that just means that you need to be more careful about the allowed momenta, right? And that just changes this normalization in a certain way, which is again easy to work out. So you can work out all of this, okay? Good. So then, let's just show how this actually helps. So again, you can sort of convince yourself that the largest block that you would get if you also conserve momentum is mz equal to 0 and k equal to 0. Okay. Now, suppose you are sitting in this block, you can actually use further symmetries depending on certain spin problems which respect that. As for example, there are two simple discrete symmetries that are there. One is parity. So parity is nothing but you again have this 1D thing and you just reflect it at some point, and then that's this operation. Of course, if you do this operation twice, you'll get identity again. So the eigen values of this operation can only be plus or minus 1. So you should first note that this parity does not in general commute with the translation operator, right? So, I mean, you cannot always use parity in a very simple way for all these momentum blocks, okay? But suppose you're dealing with some specific momenta, like k equal to 0 or k equal to pi, then you can immediately see that for those momenta, actually p commutes with t. That's simply because under parity, you can show that k goes to minus k, and 0 and pi are therefore special in that way, right? So you can use that in this block very easily, and it's a discrete operation. Similarly, you can use operations like spin symmetry, spin inversion symmetry. So you just take each spin and you just invert it, right? And again, of course, you cannot use it for every possible block, because of course this operation changes your mz. It takes it to minus mz. But you can use it in the largest block that you have, mz equal to 0, right? So here I have shown a table where I'm in this block, k equal to 0, mz equal to 0, and this first quantum number refers to parity, the second quantum number refers to spin inversion symmetry. So of course there are 4 combinations here, because both these numbers can be plus or minus 1 if you go to the right block. And so these are the number of spins that you have. So you can clearly see the way the size of this reduced block goes, right? So of course the total Hilbert space goes as 2 to the 8 here, 2 to the 32 here, and so on and so forth. But you can see that these numbers, of course, ultimately go exponentially fast again, but they are not growing so much faster, right? So even for size 32, these are manageable numbers if you do if you write a reasonable code. So in principle, you can access this information. And if you go to some other quantum number sector where maybe k is not 0, maybe k is something else, pi by 4, then the blocks are even smaller, right? So you can access all this information by doing some clever thing at the outset. Good. So now, well, there's another standard thing called Lanczos algorithm. Actually, for details of these eigenvalue solvers and Lanczos algorithms and so on and so forth, I can actually refer you to this very nice review article by Sandvik, where he gives even pseudocodes. So pseudocodes are not real codes, it's just programming logic. So anybody can follow that logic and write his or her own code. Okay? So basically this Lanczos algorithm deals with not trying to get the full eigenspectrum, but certain low-lying states. And there is a very well-defined way in which it can be done. And typically with Lanczos, you can go to bigger system size, typically twice of what you can go to with full diagonalization. Okay, so maybe you can go till n equal to 40 spins for a spin-half system. So skip these details, and I would want to show you how to apply this. Okay, so let's take the first problem that we want to address. So let's say I take my Heisenberg spin chain, but also put next nearest neighbor antiferromagnetic interactions on it, right? So this is the famous J1, J2 model in 1D, spin half J1, J2 model, or it's also known as the Majumdar-Ghosh model in 1D, right? So now, when this J2 term is very small, let's actually put it to 0, then it's known that the spin-spin correlations as well as the dimer-dimer correlations in this model are critical, okay? And there are, in fact, power law interacting spin-ons in this model, and their dispersion is also analytically known by a Bethe-Ansatz solution, okay? And that's their dispersion. Now, suppose you go to the large J2 limit. In the large J2 limit, basically the ground state is completely different. The ground state is in fact a valence bond solid, if you wish, and it breaks translation symmetry. So these are the two cartoon states, okay, if you wish. So Again, this problem has periodic boundary conditions, so it's on a ring. So you can imagine forming a singlet like this, or you can imagine forming it the other way around. So that's a cartoon of the two possible symmetry broken valence bond states, right? So at one end, there's a symmetry broken state, and at another end, there's a critical state, if you wish. And there's a very interesting phase transition in between, which is roughly, so this G is the ratio of J2 over J1. So you tune this G, and there's a critical transition here. Okay. So now, let us try to locate this critical transition using ED. It might appear very difficult, but we'll see soon how to do it just by looking at the correct excitations. So let's identify what are the lowest excitations in both these two phases. So for the critical phase, which is basically if you have J2 being very small, you can actually convince yourself that the lowest excitation is a triplet which lives at momentum pi. Okay? And in the thermodynamic limit, it's a gapless mode, but in a finite system size, of course, it's gapped, and this gap decreases as 1 by n, where n is the number of spins here. Now you go to very large G, you know that there is this discrete symmetry breaking here, and you can again convince yourself that the lowest excitation above the ground state is now completely different. It has different quantum numbers. So it has the same momentum, k equal to pi, but the spin quantum number has changed. It's s equal to 0. It's a singlet excitation now. Okay? And the gap, because this is a discrete symmetry breaking, goes exponentially in n. It decreases exponentially in n. Okay? Good. So now, all you need to do is track these two energy gaps as a function of G. Right? So when you are, yeah. Oh, I see. Right. So see, here, sorry, I still have to get a hang of this pointer. Here, if you're in the large G limit, right, these are your two ground states, if you wish, right? So, of course, this is just a cartoon state, and this is also just a cartoon state, but you can form effectively a superposition of these things like this, and this becomes your ground state, and this becomes your first excited state. Okay? And the gap basically refers to the energy difference between this state and that state. And that goes exponentially small in n. And that's the lowest gap in your spectrum. Okay? And this is true for most discrete symmetry breaking problems. It always goes like this. Okay? Good. So now, you just calculate these gaps. So that's exactly what I have shown. So if you just concentrate on the dotted line and the red line, you just calculate these gaps and just study their evolution as a function of G. Now you see, so this is for size 16. You can use Lanczos to go to much bigger sizes, approximately 40 or so on. So you can see that there is a crossing at some point. And that's very easy to understand because, you know, if you go to one limit, you know that one of the gaps is actually smaller. If you go to the other limit, you know that the other gap is smaller. So there must be a crossing in between. And now, if you track this variation of this crossing point as a function of system size, then even with the resolution of data till n equal to 40, you can do a very nice finite size extrapolation and get the critical point in the thermodynamic limit. And if you do this extrapolation, this is the critical point that you get, just by doing ED. And you can see that the error bar is on this digit. Right? So you can see that this is a highly accurate thing, but of course, to get this thing, you need to look at the right quantity, right? Okay. I mean, this is true for everything in life, right? I mean, for anything complicated, you have to look at the right quantity, because otherwise you're lost. So, right. Good. So the next thing that I want to highlight, I can already see I'm running short of time, but it's okay. I'm also around, so you can ask me questions later whenever you feel like. So the next thing I want to talk about is detecting spontaneous symmetry breaking in a finite system. Now, this is also a very powerful technique. So, I mean, let's imagine that there is a continuous symmetry breaking in my system. Just for concreteness, you can imagine the 2D Heisenberg model on the square lattice, then we know that in the thermodynamic limit, there is a nail order there. And the nail order breaks, spontaneously breaks spin rotation symmetry. So then you can ask, how can I detect that in a finite size system? Is there any signature in the excitation spectrum? It turns out that for any kind of continuous symmetry breaking, there's actually a very interesting signature in the eigenstates, which is known as the Anderson tower of states, and this is as follows. So I just show it for the 2D Heisenberg model. This is Lanczos data again for n equal to 32, but you can see that now the data has been arranged in terms of the total spin quantum number here, right? So the first thing to realize is, as has been indicated here, there are some states which are much lower than all the other states in this spectrum, right? And these states have a particular scaling. So you can see this dotted line here. So the scaling is actually S total times S total plus 1 divided by n, where n is the number of spins in your system. So the first thing is that there are these tower of states which actually scale much faster than any other states here, and they crash to the ground state as 1 by n, okay, where n is the number of system size. So for a two-dimensional system, that'll be 1 by L square. For a three-dimensional system, it'll be 1 by L cube, where L is the linear dimension. Whereas the Goldstone modes of your system scale as 1 by L. And these are your Goldstone modes, you can see. And they are also separated by these other states. So you can actually do a lot here. You can look at the quantum numbers here, and you can actually show that if there is a nail symmetry breaking, then what you will get is that these tower of states will only come at two momenta, 0, 0 and pi, pi on the square lattice. And you will see that at k equal to 0, 0, you will get the even S states. So these are these blue guys. And for the other momenta, you will get these odd S states, okay? And the nice thing about this is that you can actually do a lot more here if you know the particular continuous broken symmetry. For example, using this method, you can detect more complicated order, like nematics, okay, spin nematics. So just by doing a proper symmetry analysis. So for that, I refer you to this very nice review article by Andreas Leuchtli and others. And there are many more details in this article, right? Okay. Okay. If they are linearly dispersing, it should still be 1 by L. Yeah. Right. Okay. So now I move on to other things which can actually take you to much bigger system sizes. So of course you saw that the limitation of ED was that you cannot go to very big system sizes. But of course, the nice thing about ET was that in some problems, you can look at right quantities and still glean out a lot of physics. And then you can, of course, use other techniques to make more advancement. So now I come to one such very powerful technique, which is a stochastic technique, but it's an exact technique, which is Monte Carlo methods. Okay? So basically, the idea of any Monte Carlo algorithm is that there is some configuration space, and one has to devise a random walk in this configuration space. Okay? And that's your Markov process, if you wish. And this random walk takes place through some predefined probabilities. So if I give you a state C1, then there is a certain probability to go to C2, there's a certain other probability to go to C3, and so on and so forth. And basically, it's a Markov process because these probabilities do not depend on any prior history of how the system landed up in the state, for example, Cn. Okay? Furthermore, if such a Markov walk satisfies two further conditions, so the two conditions are, one is the condition of ergodicity, which simply means that if I give you some configuration Cn, there must be at least one pathway in this process of going from that configuration to any other configuration that you want in phase space. Right? So that's ergodicity. The second condition is the condition of detail balance, which says that suppose you want an ultimate target probability distribution. So this is effectively a random walk. And this random walk, you can imagine, is like a non-equilibrium process, and that non-equilibrium process is taking you to some final equilibrium. And when that final equilibrium happens, to ensure that the states are coming with the right probabilities, you have to ensure this equation, which is the principle of detail balance. So given any two states in configuration space, let's say Cn and Cm, the probability to go from Cn to Cm and the probability to do the reverse should be connected by this equation, where this P of Cn is the final target distribution that you want. Of course, if you are in equilibrium, we very well know what this final target distribution is. This is just the Boltzmann distribution, the canonical Boltzmann distribution, right? Okay, and then that's it. In principle, this all looks very easy. Then you just follow this random walk, and you can just take a simple arithmetic average of any sort of object or operator that you want to measure, and you take this averaging for a sufficiently long Markov chain, and then you get the estimator for that at a finite inverse temperature beta. Okay, so that looks very straightforward, but there are of course many caveats. So well, the simplest sort of algorithm, which I'm sure all of you have heard about, is the Metropolis sampling. And this you can apply, for example, to the 2D Ising model. So in the Metropolis sampling, the way you satisfy detail balance is the following. You basically just need to specify the probability of choosing a particular spin. So you just randomly go to a spin, and then you try to flip it. And when you flip it, you monitor its changed energy, the changed energy of the system. And if the energy increases, then you basically pick that configuration with this probability. And if the energy decreases, you always pick it, right? And so just in terms of mathematical equations, this is the meaning of the statement that you pick a spin at random. And this is the meaning of just the physical process that I told you now. And you can verify that these two things satisfy both detail balance and ergodicity just by plugging it into the previous equation, right? Okay, so if you do this process sufficiently long, for a sufficiently long amount of time, your system is guaranteed to reach equilibrium. Good. However, there are some caveats here, so I should like to mention them. So you see, one very important thing about any Monte Carlo process is that you need to do a random process over and over again. That's why it's stochastic in nature, right? So you need random number generators to do that. Now, my advice to you is please use a good pseudo-random number generator. And again, there are many free ones available, so you don't have to pay money. I hate paying money for these kind of things. So, so you can, for example, use something called Mersenne Twister, which has a very large period. You can use something else, which was invented by Martin Lucier, who's a high-energy physicist. That's called RANLAX. That's even better than this. So all these random number generators, these more advanced ones, are based on some generalization of simple chaotic maps that we have studied in classical mechanics. So they are based on some very high dimensional generalization of that. But I don't want to dwell into that. You can read a lot of literature into that. But see, if you don't use a very good random number generator and you do high precision Monte Carlo, just by using proper statistical analysis, you can figure out that your random number generator is bad. Okay, so I would refer you to this very nice paper by Landau, Wang, and Fehrenberg, where they actually, this was in 1992, they actually used the 2D Ising model example here. And in the 2D Ising model, you know that there is the Onsager solution, so certain things can be calculated exactly on any periodic lattice. So they did that, and then they compared their Monte Carlo data with the correct error bars on their data, and they compared it with the exact answers. And they could actually show that some random number generators are good and some are bad. Because, of course, if your random number generator is good, you should see that the answer actually falls on the correct answer. So this is actually a very interesting paper to read. Okay, good. So now, again, it seems that everything is simple and straightforward here. I just give you an algorithm and you can just happily do your coding and get everything you want. But there is a problem. So see, this is a stochastic estimator, right? So for this estimator to have a small error bar, what you need is a large number of decorrelated samples when you move through this Markov process, right? Because that is what gives you smaller and smaller error bars. Roughly, the size of your error bars goes as the square root of the number of decorrelated samples that you have, right? It's very important to get decorrelated samples. Now, you can ask, oh, is my Monte Carlo process, this dynamical process that I'm doing, is it sufficiently good at decorrelating the system at whatever temperature and system size I'm looking at? That's a very relevant question to ask. So then, for that, you can look at something called the autocorrelation function, which is defined in this manner, okay? And this autocorrelation function has the property that when things become decorrelated in Monte Carlo time, it just goes to 0. Okay, and you can show that asymptotically it has certain behaviors like this. It goes exponentially to 0 after a certain time. And this tau O gives you the characteristic decay time of the relaxation process in your Monte Carlo. So now, of course, if you're again studying the Ising model and you're only concentrating on low temperatures or high temperatures, there are many other methods to address that problem. For example, you can just set up some low temperature expansion or a high temperature expansion, right? So why do you want to do this song and dance? So you want to do this because if you're near the critical point, then it's much harder to do the problem through these perturbative techniques. But then you use this Metropolis algorithm and you measure the autocorrelation functions and you see something very dramatic. So this is the data of the Metropolis algorithm at a temperature which is bigger than the exactly known transition temperature for the 2D Ising model. You can see that reasonably quickly the autocorrelation time converges. You can just read it off from the slope, right? So you can see it converges rather quickly to some number. Okay. Now you go to a temperature which is very close to the critical temperature, which is exactly known in this case. Then you can see that as you go more and more in system size, the autocorrelation of the order parameter. I'm sorry, I forgot to mention that. So I'm looking at the autocorrelation of the order parameter, which is just the total magnetization here. So you can see that this autocorrelation time actually increases significantly with increasing system size. And that's actually known as critical slowing down. And you can actually be more precise than that. You can show that the autocorrelation scales as L to the Z, where Z is some kind of a dynamical exponent, and it's close to 2 here for this Metropolis algorithm. So this is a property of any local algorithm that you take, near critical transitions, second order transitions. So why am I saying that the Metropolis algorithm is local is because the fundamental move here is just flipping a spin, and that's a local move. So in that sense, the dynamics is local. So you can see that clearly you cannot go to very big system sizes because, of course, you can run your Monte Carlo to as big a system size as you want, unless you run out of memory, but then whatever data you have will have huge error bars, right? Because of this problem. Good. However, at least for unfrustrated systems like the Ising model in 2 dimensions on the square lattice, you can solve this problem to a significant degree by taking what are known as cluster algorithms. And then you can even simulate a huge number of spins. So just to give you an idea, you can simulate a system of roughly 1,000 cross 1,000 spins on the 2D Ising model in the critical regime using this a particular cluster algorithm invented by Wolf. So this is a huge system size, and you can basically get things to very small error bars, which just means that you can basically get all the information of correlation, susceptibility, specific heat, and so on and so forth to as high an accuracy as you want, right? But this is only for a unfrustrated magnets. For frustrated magnets, the story is a bit more complicated, and you can show that even in the cases where you can formally write a cluster algorithm, if you look at its performance, it's not much more better than a local algorithm. So that's another big open challenge in the field. How can you write good cluster algorithms for frustrated magnets? Okay, good. There are some techniques which, even with local algorithms, can give you high speedups. So I would just not mention it in detail. I would just like to mention that there's something called parallel tempering, where what you can actually do is to just realize that if you have a finite system and you just draw its probability distribution in energy, right? Then suppose I draw the distribution at temperature T1, T2, so on and so forth. You can see that T1 and T2 have overlapping regions, right? That just means that a configuration at T1 with a certain reasonable probability is also a configuration at T2, right? And so on and so forth. Of course, if you see something at the tail here of T1, and then you ask, is it a configuration of T5? Of course, the answer is yes, but that event is a very small probability event, right? But if you pick temperatures like this, you can in principle do jumps in temperature space as well, which satisfies detail balance, and then you can, to a certain degree, solve the relaxation problem of local algorithms. So this has been, for example, very beneficial in spin glass problems. Because spin glass is a very challenging problem where the timescales increase dramatically. But with this method, at least certain classes of spin glasses could be handled on a computer, and people could ask questions about finite size scaling and so on and so forth. Okay, good. So let me show you some interesting examples now of non-trivial physics that you get just by doing this classical Monte Carlo, right? So one of the examples is this. Now, suppose you don't take the 2D Ising model, because that's an exactly solvable thing, so you might still ask, what's the use of that? I can always write the Onsager solution. Now, let's say you add some next nearest neighbor couplings onto it as well. Let's call that J2, and let's say that J1 is ferromagnetic and J2 is antiferromagnetic, right? Then that's the J1, J2 Ising model, and that's already a problem which you cannot analytically solve. At least till now, we don't know of any analytic solution of that problem, okay? Now, in that problem, you can show that there are very interesting phase transitions. In fact, if you look at the finite temperature phase diagram of that, so please ignore these lines. This is with disorder, but let's just talk about the clean limit here. So of course, if this J2 is very small, you're almost back to the Ising problem. So there's a thermal phase transition from the ferromagnetic to the paramagnetic phase. However, if you're in the large J2 limit, then you can show that the broken symmetry is completely different. Basically, the system breaks up into stripes like this. So these are, if you wish, up spins, down spins, up spins, down spins. So they just line up into stripes. And this phase breaks lattice translation symmetry. Now, this symmetry, the order parameter here is, if you wish, a Z4 order parameter. But you can show that in 2D, just saying that your order parameter is Z4 is not enough to tell you what the correct critical theory is. So in this model, what happens on this side, what is the phase transition on this side, was actually controversial for a very long time. But finally, we know the answer now. So what happens is, initially there is a very weak first order phase transition, and this answer was basically known due to Monte Carlo algorithms. Okay, there's still no analytic technique to give this phase diagram. So, so from G equal to 0.5, which is the ratio of this, to about 0.7, there's a whole line of very weak first order phase transition. I mean, this phase transition is very weak, and we still don't know what's the correlation length here. It's so weak. And then the transition, the universality crosses over to something which keeps changing with the strength of this coupling. So here the transition is in the Q equal to 4 Potts model at this tri-critical point, if you wish, at 0.7. And then ultimately it goes to Ising. So, and this problem, the universality of this problem can be mapped to another very well-known problem in StatMech, which is known as the Ashkin-Teller model. And there people know some things analytically, and this mapping from this problem which you cannot solve to this problem which you can solve at a universal level can be done through Monte Carlo, right? So that's one interesting application where there is no analytic solution. So another thing which you would probably hear several talks which happens in frustrated magnets is this order by disorder. Right? So let me give you an example of that, which was also detected very nicely through Monte Carlo, classical Monte Carlo algorithms. Good. So, so now let's take again the same J1, J2 model, but let's not take it on an Ising problem. Let's take it on a Heisenberg problem. Then, again, if you go to the large J2 by J1 limit, you can show that the ground state is very interesting. Again, it just breaks into two decoupled sublattices, and on each sublattice you have its own nail order. So even though the symmetry of the Hamiltonian, if you wish, is O3, the symmetry of the ground state is actually O3 cross O3, because it breaks into two decoupled lattices like this. And then, of course, there is always a possibility of order by disorder, because the symmetry of your ground state is, in fact, more than the symmetry of your Hamiltonian. Right? So there's nothing to intrinsically protect it. Okay, good. So actually here, in this paper, and this idea was theoretically proposed by Chandra and others earlier for this particular model. In this paper, what they showed was, so you're starting with a model which has continuous degrees of freedom in 2D, right? So of course, there cannot be a spontaneous symmetry breaking of this continuous symmetry because of Mermin-Wagner theorem in 2D. However, what you can show is if you're greater than G equal to 0.5, as you go to low temperature, there's actually a non-trivial phase transition into some discrete degrees of freedom. And this is the order parameter they looked at. So you can imagine defining a plaquette, and these I, J, K, L live on the plaquette. And basically, at low temperatures, what happens is there are some collinear structures which are preferred. And at very low temperatures, there's in fact a Ising phase transition into some object like this. So this object, in fact, becomes non-zero. So you actually break a Z2 symmetry at low temperature. But of course, you don't break any continuous symmetry. And so this is actually the susceptibility of this Z2 order parameter. You can see that as you increase system size, there's a nice peak which is characterizing phase transition. And then using this and other techniques, they could estimate the phase diagram of this problem. So at low temperatures, the physics is that of ordered stripes, if you wish, but disordered spins. Okay, so that's another nice example where this Monte Carlo technique helped a lot. Then the third example, and then I move to quantum Monte Carlo, which I would like to give is interacting dimers in 3 dimensions. Now, classical dimer models, I'm sure many of you are aware of this, are basically models where the fundamental object is a dimer, and basically the constraint is that no two dimers can touch each other. Right? And then you just imagine a close packing of all these dimers. You just put in as many dimers on the lattice as is possible without actually breaking this constraint. That's a close packing problem. Then you can ask, okay, suppose I give a Hamiltonian to this problem. So the Hamiltonian in this case is, so there's a 3D dimer model living on the cubic lattice, and the Hamiltonian is that on any elementary square plaquette, if you have two dimers aligned on any elementary plaquette, there's a favoring of energy. So the Hamiltonian wants dimers like this, or like that, or like that, right? So there are 3 possibilities, right? Good. So now you can show that at high temperature, basically you can forget about energy, then it's just a close packing of dimers. But that problem is also very rich, and that problem does not break any local symmetry. But that problem has algebraically decaying correlations. Okay, so this is well known for dimer models without any Hamiltonian. However, if you go to very low temperature, because your energy function is like this, these dimers are just some degrees of freedom which live here. I mean, that's it. They are not hardcore cosons. This is just a classical problem. Well, you can cook up some effective classical magnetism problems which map to this, but That's not very important. It's just a model with interesting physics. Okay, good. So now, for these dimer models, okay, as I was saying, at low temperature, you can then show that there is again an analog of a valence bond solid here, but of course, this is purely due to this classical effect of this packing and the energy. So the dimers line in a particular way at low temperature so as to break translation symmetry. Okay, so at low temperatures, there's a broken symmetry phase. At high temperatures, there's a phase which breaks no symmetry. Then you would say, oh, I understand everything. I can just use Landau theory and characterize this phase transition. But it turns out, if you look at this problem with Monte Carlo, as was done by Fabian, Ale, and others in 2006, the phase transition comes out to be something which cannot be understood in a Landau theory. And the reason for that is, in the high temperature phase, which is the phase which has no finite order parameter, nonetheless there is an algebraic decay of several correlation lengths. So it's a highly correlated phase, right? So you cannot capture such kind of physics always in a simple order parameter theory. So in fact, this was first shown numerically like this. So firstly, this is specific heat data per site. Now you can see that there are two peaks here, but the bigger peak has an interesting property. You go to bigger and bigger system sizes and the peak just falls on top of you. So there's no phase transition. But you see that there is this smaller bump here. And you zoom in here, and they could see that there's actually a genuine continuous phase transition. And they could do very nice finite size scaling and so on and so forth. And they could show that this is a non-Landau phase transition. Further evidence of that in a related model was obtained recently in this work by Srijit, Powell and Adam Nahum, where they could actually show that there was, in fact, emergent symmetry at this critical point, and that also basically tells you that this is a non-Landau phase transition. And in this paper, this archive version that I've quoted here, they in fact discuss the connection of this phase transition to the two-dimensional deconfined critical point transition. Okay, so if you're interested, you can look at that. Good. So that's so much for the classical Monte Carlo. Now we come to quantum. Yeah. The bigger peak, yeah, I understood it at some point. Now I forgot. Is some crossover physics. It was some crossover physics, and yeah, and that's why it's saturating. But I have to relook at this thing. Yes. Okay. Yeah, there is a material, see, I mean, I will show you later on some quantum problems where these are like XXZ models, right? Where if you push the Z coupling to be very high, then these go to some limits where it looks like classical dimers. However, there, if you perturb the problem by turning on XX, then it induces quantum fluctuations. Well, but similarly, you can think of classical problems where you add, instead of that Z, some other higher spin interactions in Z, and they can give you interactions in timers. So it is possible to cook up some things. I mean, I can write a Hamiltonian for you. You have to then tell me, yeah. This is different. Yes. Right. But we can discuss this more later. Yes. Okay, good. So now, in the remaining, how much time do I have? 10 minutes. Yes. 10 minutes and maybe plus 2 minutes. I'll try to explain to you about quantum Monte Carlo. Okay. Now we immediately land up into a conceptual problem. See, in the classical problem, I told you that there's a Markov process, and you go from C1 to C2 to C3 to so on and so forth. For the Ising problem, C1, C2, C3 are just physical spin configurations, right? Now, for a quantum system, what do you mean by these spin like physical configurations, and how do you even think of a Markov process in that language? So for that, it's actually essential to map this quantum problem to an effective classical problem. Okay? So for any quantum Monte Carlo, well, for most quantum Monte Carlos, you basically have to first map the quantum problem to an effective classical problem, and then you think of trying to devise a good stochastic Monte Carlo algorithm for the effective classical problem. That's more or less always the case. Okay? So in view of time, and also because of my own knowledge, I would just briefly expand on this very nice method called stochastic series expansion method for spin systems. This works very nicely for spin systems. But of course, if you have to do fermions, you take other methods and so on and so forth, right? Now, there's a very big issue here. See, I map it to an effective classical problem, and maybe it gives me some effective probabilities. But many a times you can show, and I'll give an example later on, many a times you can show that this mapping can give you probabilities which for some configurations, I'll of course have to tell you what a configuration is now, which for some configurations are actually negative. So then you cannot think of it as a conventional static problem, because of course all the probabilities have to be positive in that. And that's basically the notorious sign problem. And this sign problem often happens for a frustrated spin system. For some spin systems, there's a way to get out of it. For other spin systems, we still don't know of a way to get out of it. But there's an important point here. The point is the following. See, suppose you're after a phase or some phase transition. Many a times, not always, but many a times, it might be possible to think of another effective model which has no sign problem, but that shows the same physics at low temperature. And then you can try to understand the universal physics from that direction. Okay? So that's point number one. And point number two is, this sign problem and how severe it is actually a basis-dependent statement. So there have been quite a bit of progress in the community on trying to tweak what is the basis that you take in your Monte Carlo and how can you sort of reduce the sign problem with that. But that's an entire field in itself, which I can discuss later in private. But that's another very fascinating thing to think about. But probably there is no general solution to this sign problem. Okay? I mean, there are reasons to believe that, which I think are fairly solid. Okay, good. So, okay, I think I'm running out of time. So let me just show you some examples instead of giving you this heavy-duty thing. But you can always look at my slides and you will see, if you look at them, that if you just follow certain conditions, and if those conditions are respected, you can write a stochastic series expansion, right? So it's, yeah. If those conditions are true, you can just write your algorithm. Okay, good. And it's not very difficult to write it. Okay, good. So let me just say a word about the sign problem thing. So one way people sometimes say that you can resolve the sign problem is, see, as I told you, there is some stochastic process that is taking place. And unfortunately, I didn't explain and expand on what this effective classical problem is, but I can do it in private. So there are some probabilities associated with this problem, with this effective classical problem. So imagine that, okay, if all these probabilities are positive, then you're happy. At least you can think of writing a Monte Carlo code. Again, your code might not be too efficient. That's a different problem. Well, that's not a different problem in the sense that you're then again stuck. You cannot go to a big system size. But at least in principle, you can start from somewhere. So, however, if some of these p's are negative, then one thing which sometimes is attempted is, you don't sample with pi, you sample with mod of p. And that's a positive. However, you see, the statmic problem which gives you this pi and the statmic problem which gives you mod of pi are two different physical problems, right? So let's say the problem which gives you pi has a free energy of f, and the problem which gives you mod of pi has a free energy of f of mod of p, and this is a non-zero quantity because these are two different problems. You can then show that because these are two different problems, if you actually then look at how the error on some local quantity in your Monte Carlo scales, you can show that basically this scaling becomes exponentially bad in inverse temperature and volume of the system size. So this is an NP hard problem. There's no way to beat that, no general way to beat that. You can beat it in some specific cases, but there's no general way to beat it. Okay, good. But there are enough of interesting problems with unfrustrated lattices. So in the remaining 5 minutes, if the chair permits, I'll just show you 3 examples of problems which are unfrustrated, but which gives very interesting phases. So, Okay, so this is a problem on the triangular lattice. So the problem can be thought of as an XXZ model. So the dominant interaction is the SZ-SZ interaction on the triangular lattice, and it's antiferromagnetic. Now, it's well known in classical StatMech that that problem is disordered down to 0 temperature and has interesting algebraic correlations. And one way to see that is to map it to a dimer model, and you can solve that dimer model problem, so on and so forth. Now, suppose you add quantum fluctuations on top of that model. So let's say you add ferromagnetic transverse coupling, right? If you want, you can also think of it as a boson problem like this in terms of hardcore bosons. So this U is like a Hubbard term, and this T is like a Hawking term of boson. Then, if you actually crank up this U term, you can actually show that, of course, for small u, it's a superfluid, or in terms of a magnet, there's a ferromagnetic component. But as you crank up u, there's a very interesting supersolid phase that is obtained. And this phase was first observed by using Monte Carlo simulations by these 3 groups simultaneously. And this is a very interesting phase where there is a simultaneous occurrence of a solid order parameter and a superfluid order parameter in a lattice model, even when the correlation is very strong. So this is a robust phase. Okay, good. So that's one example. The second example is that of a Z2 spin liquid on a Kagome lattice. So again, you can write some spin problems where there is no sign problem, but you can stabilize a Z2 liquid on the Kagome. So here, these symbols just mean that you go to the Kagome lattice. Oh, I haven't drawn a Kagome lattice. But as you know, on the Kagome lattice, there are these hexagons, right? So you just sum up the spin components on the hexagons, and you just square that, and that's your Hamiltonian. Okay? Or you can think of it as an equivalent hardcore boson model again. Here, it was first shown by Isakov, Yombeck-Kim, and Arun Paramkanti in 2006, that if you again crank up this ratio of V by T, you actually land up with a phase which breaks no local symmetries. And it's actually, with various arguments, they could show it's actually a topological spin liquid, which is a Z2 spin liquid. In fact, much more recently, there's a series of work by Matt Hastings, Roger Melko, and others, where they have come up with a way of directly measuring Renyi entropy using quantum Monte Carlo simulators. So this Renyi entropy, using Renyi entropy, you can extract some things about this topological entanglement entropy, which Yogesh was mentioning about. So at least, even though you cannot experimentally measure it, you can measure it numerically. And then for a Z2 spin liquid, these Renyi entropies have certain properties, in the sense that there is a term beyond the area law which has to attain an exact number of a log 2 and a 2 log 2 and nothing else. Okay, so then there were these Monte Carlo simulations by the group of Melko where they could actually show that. Well, they haven't yet shown that it goes to 2 log 2, but hopefully they'll show it soon. Okay, but at least even this is very non-trivial for this phase. Okay, good. So that's another interesting example where you can construct a magnetic problem which is frustration-free and try to understand the physics of a Z2 spin liquid using much bigger system sizes than you can using ED, for example. It'll miserably fail here, right? So, good. So here's another example. So one thing which we always learn in StatMech is that if you look at a quantum phase transition, there is a way to map it to an effective classical phase transition in one higher dimension. So here is a very nice example which shows exactly that, and that's why I've called it quote-unquote conventional quantum criticality. So this is a very famous problem called the Heisenberg bilayer problem of spin half. So basically it's nothing but 2 coupled square lattices, and there is a usual Heisenberg coupling in plane, and there's also Heisenberg coupling out of plane. Okay, and then you can actually drive a phase transition from a Néel phase to a trivial paramagnet here. So this word trivial is very important. So it's a paramagnet, but it's not a spin liquid. Okay, it's a trivial paramagnet. You can write its wave function as a product state if you wish. Okay, then you can actually show that the phase transition here is exactly in the same universality class as the 3D classical Heisenberg model. And this is exactly the expectation from this quantum to classical mapping. Okay, and this was shown in a very beautiful paper by Wang, Beach, and Sandvik, where they could do very precise finite size scaling to attain the exponents and the critical point. Okay, so this is another case where quantum Monte Carlo was really important to show this. Now, the last example I come to is an unconventional quantum phase transition. Right? So what do I mean by that? It's unconventional because this Landau paradigm does not work. That's it. Okay? But we can talk more about this later. So there is this class of models which was originally invented by Sandvik in 2007, which basically has certain four-spin interaction terms which mimic ring exchange in some ways. But these terms are constructed again so that you don't have a sign problem and you can do quantum Monte Carlo. Now, in the low Q limit, again, there is a Néel phase here. But in the large Q limit, there's actually valence-Born solid phase here. And this valence-Born solid phase spontaneously breaks translation symmetry. So these are actual singlets here. Okay? And there are four possible sort of symmetry partner states here. So now, what miraculously happens here is the Néel order parameter goes to 0, and the valence-Born solid order parameter comes up to a non-zero value exactly at the same point. So you see, on the face of it, these are two completely unrelated order parameters. One lives in spin space and basically is characterizing broken rotational symmetry. The other lives in lattice space and it's just characterizing a translation symmetry breaking. So on the face of it, you would never expect a continuous phase transition between these two situations. You'll always expect the first order phase transition. But actually here you can show that there is a genuine continuous phase transition here. Again, this was done using quantum Monte Carlo, and you can show that to a very high precision, this thing and this thing happens together. Not only that, there is a very interesting physics when you go in the neighborhood of this critical point, and that is that you cannot write down you can always write down an order parameter description, but the reason the order parameter description fails here is that basically the order parameter fractionalizes into some fractional excitations called spin-ons here, and then it's more appropriate to think of the theory in terms of these spin-ons. Okay? And then there are various non-trivial things which happen near the phase transition, and all of this has been, for example, detected by quantum Monte Carlo, right? So basically, I hope I have given you some examples of how these numerical techniques can give you very non-trivial information about strongly correlated phases, also about phases which are conventional. For example, now there are methods you can even detect the dispersion of Néel phases using quantum Monte Carlo, and so on and so forth. I haven't had time to discuss that. So at the end, I would just leave you with some references, and there were also some references during the talk. So these are all very nice papers and books, so you can read them if you're more interested in anything. Okay, so thanks for your attention and patience.